Welcome to the lecture. My name is Sonain Jamil, registration number 16T16. Today we will discuss about moving averaging filters. First of all, we will discuss what are moving averaging filters and their implementation by convolution, noise reduction versus step response, and what are the relatives of moving averaging filter, then recursive implementation. Moving averaging filter is very simple and most common filter in DSP. It is very easy to design and it is the very simple filter. Now, how it is implemented by convolution? Moving averaging filter can be implemented by convolution, and its mathematical formula is this one. Now let's have a little activity on MATLAB. Let's suppose I have this signal and I want to apply a 3-point moving averaging filter. This is 3-point moving averaging filter. Now I want to find convolution in time domain. Just write conv command and then type this one. This is the convolution in time domain. Now I want to apply the FFT and then I want to see that how the convolution in time domain is multiplication in frequency domain. Just I am going to prove you. Now just applying FFT on X, 8-point FFT on X. It will be like that. If you want to see in a better way, just apply transpose, and this is the first Fourier transform of the X, the signal. Now I want to apply FFT on the response of the filter. What I will have to do is just write this, and this is. Now I want to multiply both these. As I said, convolution in time domain is multiplication in frequency domain. Just apply dot product and this is the result. Now if I apply inverse FFT to verify that whether the multiplication in time domain is convolution in frequency domain or convolution in time domain is multiplication in frequency domain or not. So just if I want to find the transpose of this, a little bit mistake. I am going to compare both in a small y transpose, sorry, and y1 transpose. If I want to show you why this is y and this is y1, as you can see that these are similar. This is 2 minus 1, as you can see that 2 minus 1 0, 2 3 3 minus 1 1 minus 1 1. So multiplication in frequency domain is convolution in time domain. Now let's start with the lecture. This is the formula for moving averaging filter, and we implemented it with convolution. Now noise reduction versus step response. First of all, if we want to remove the noise from this signal, if we apply a 11 point moving averaging filter, what does it mean? 11 point moving averaging filter means that it has 11 ones in h of n, the response having 11 one impulses. So it will have good step response, but attenuation is not good. But if we apply a 51 point moving averaging filter, it will be smooth, but it will have slow step response. So there is a trade-off between both these. the This is very simple, but engineers always are reluctant to use a moving averaging filter in applications. So what is the frequency response? As I told you, moving averaging filter is a rect in time domain. So in frequency domain, it will be a sinc function. What are the relatives of moving averaging filter? The first one is Gaussian filter, and the second one is Blackman window filter. If we have a moving averaging filter and we pass first time the signal from this moving averaging filter, and then we apply again moving averaging filter on that signal, the resulting filter will be known as Blackman window filter. If we pass 4 times that signal from the filter, and the filter is known as Gaussian filter, and the representation in time domain is like this one. In the first is 4 pass is Gaussian filter, 2 pass Blackman window filter, the first one is moving averaging filter. So as you can see that Gaussian filter have a slow roll off, but it has no stop band attenuation, while Blackman Windows filter has relatively slow roll off but attenuation. Blackman filter have fast roll off but attenuation, while Gaussian filter have slow roll off with no stop band attenuations. Now, if we want to implement a moving averaging filter, how we can implement it? The another method is recursive implementation. Most recursive filter have an infinitely long impulse response, IIR, composed of sinusoidals and exponentials. The impulse response of the moving averaging filter is rectangular pulse, as I told you. If we want to see the example in the book, it will be like if we have a 7-point moving averaging filter and we want to implement a recursive implementation, as you can see that y of 50 is equal to x of 47 plus x of 48 plus x of 49 plus x of 50 plus x of 51, x of 52, x of 53, and y of 51 is what? Just slide shift. So if we just subtract x of 47 from y of 50, this is this one. If we subtract only this thing from this and add x of 54, the result will be y of 51. So this filter having finite impulse response will be implemented by this equation having infinite impulse response. As you can see that in the general form it is represented by this equation. There is a note. Notice that this equation has two sources of data. The output, previous output, and the inputs. Previously calculated points from the output and points from the input. As you can see that this is the line. This is called recursive equation. So this equation is known as recursive equation, meaning that the result of one calculation is used in future calculation. As you saw that we use the previous output to find the next future output. There are the advantages of this algorithm. This algorithm is very fast than digital filter for several reasons. The first, let's study the reasons. There are two computational there are two computations per point regardless of the length of the filter. There are only two computations, as you can see that the input and output in the equation. The second, addition and subtraction are the only mathematical operation needed. As we saw in the above equation, the only mathematical operations are addition and subtraction. While most digital filters require time consuming multiplication, and the third is the index scheme is very simple. This one, the index scheme is very simple. Equation 15.3, this is, as you can see that the indexing is very simple. Fourth, the algorithm can be carried with integer representation. Only integers. Depending on hardware used, integers can be more than a order of magnitude faster, floating points, etc. So this was all about moving averaging filters. That's it for today's lecture, and thanks very much for watching. In the next lecture we will study Windows filter.